Okay, so we had already shown that if there is a torque on the system, the torque gives us the rate of change of angular momentum. Well, this is analogous to if you have a force acting on the system, it gives you the rate of change of the total momentum of the system. This is the total angular momentum. Now, this is the linear case, linear motion case. This is the rotational motion analog of the same equation. Now, of course, this torque can be caused by internal forces or external torque forces. The torque we had described as the sum over I, the position of the ith mass, ith part of the system, cross the force acting on the ith part of my system. This is how we define the total torque of the system. Now, this force has various parts. It has the force acting on the ith part of the system. It can be caused by other parts of my system. The force caused by on the ith part due to the jth mass. So I have my system. I have my various masses. This makes my whole system. The force acting on this one, the I, there might be a force acting on it due to this mass J over here. There might be also external forces acting on my system. This is the external forces. Now, in the case of linear moment, the change in the linear momenta, we summed over all Fi's, and Newton's third law, which said that all the forces form action-reaction pairs. These terms, they just cancelled, because for each Fij, there is an Fji, which is in the opposite direction and has the same magnitude. So the sum of the two, it just gives us 0. Now, in this case, we have this factor Ri. So if I have, let's say, this is my origin, this is my ith mass, this is my jth mass. This, if there is a force acting on the ith mass due to this one, and if it is in the in this direction, this is Fij, and this is Fji, we are just assuming that they are pointing towards each other. Now, in general, this need not be true. None of the Newton's laws tells us that this needs to be true. But for all the forces that we know, almost all of them, they point towards each other in most cases. So we will just assume that the forces that two masses exert each other, they lie on the line connecting them. Now, let's say this is my Ri, and this is my Rj. Now, when we are defining the cross products, let me write it over here. If we had this cross product of two vectors, A and B, the magnitude of A cross B was equal to the product of the magnitudes times sine of the angle between them. This is how we define the magnitude of the cross product of two vectors. Now, if you look at this B sine theta, this is nothing but the perpendicular distance of this point from this line. So this is B, this length here is B sine theta. Now let's look at over here. Or you can also think of it the other way around. This distance is also A sine theta. Now if you look at here, R cross F, Ri cross Fij. This is equal to the magnitude of Fij times the length of this Ri times sine of this angle over here, but that is at the same time the sine of this angle over here. So this product Ri times sine let's say theta I, this product is nothing but this perpendicular length. Let's just call it L. So R cross F, its magnitude is the force times this perpendicular distance. Now we can do the same thing here. The cross product will be again the force times the perpendicular component of this vector in the direction, the component perpendicular to the F, but that is also L. Since they lie on the same line, the perpendicular component of this vector and the perpendicular component of this vector, they are identical. But the magnitudes of these forces are also identical because of Newton's third law. So it just tells me that the torque created by this force is equal to, in magnitude, the torque created by this force. So these two torques are equal in magnitude. Now, if you consider the direction, what is the direction of the torque created by this force? Inside, it's R cross F points inside. The torque created by this force? Outside. It's just like the torques are also action-reaction pairs, it seems like, at least in this case. If the forces lie on the same line, connecting the masses, the torques created by these two action-reaction pair forces is also in the opposite direction, but same in magnitude, so the sum, it just cancels these two. So what it translates here is that when I take this sum, there are torques created by the internal forces, but those internal forces will just cancel, and at the end we will be left with only the external forces. So the total torque acting on my system will be nothing but Ri cross product Fi, the external force acting at the point Ri. Now, otherwise it wouldn't make any sense. Because if the internal forces were to create some torque, well, just due to the internal forces, if there's some net torque, it means that the system will be accelerating on its own. It will just start rotating on its own without any external influence. That wouldn't make too much sense. But that also implies another thing. If there are no external torques acting on my system, or there are no external forces acting on my system, then the torque is zero. If the torque is zero, angular momentum is conserved. All of its components are conserved. Now the demo time. So she already knows what she will do, right? I will just give her some initial angular momentum. Not yet. Hazır mısın? Close them. So, did you notice that when she opened up her legs, she slowed down? When she closed them in, she speeded up. Let's do it again. Yes. You have to close it down before stopping, so that they will see that you speed up. Close them. Now this was more obvious. Yeah. Well, that is an application of the conservation of angular momentum. We know that the angular momentum is conserved. And we had, in the previous hour, we had just discussed that if there is an object rotating, well, when I say angular momentum is conserved, all the components of angular momentum should be conserved. We know that there is a component of angular momentum in the direction of the angular velocity whose magnitude is given by this. So what we had observed is that as she opened up her legs and closed them up, W changed. But this product has to be conserved. What happens is when she just extends her legs, what happens to the moment of inertia? Well, there is one answer: increases. Or when you open up your arms, what happens to your moment of inertia compared to when they are just closed up? Moment of inertia is constant. Okay, there is one answer. Any other idea? Is it constant? There is one increase. Well, the other alternative is decreased. So who thinks it decreases when you open up your arms, your moment of inertia? Okay, if I don't see sufficient hands, I will force you to walk around in the classroom. So who thinks that when you open up your arms, your moment of inertia decreases? Okay, there is one. Who thinks that when you open up your arms, your moment of inertia decreases? Before it was, okay, so you are opening up your arms, the moment of inertia, let's start with increase. Who thinks it increases? Okay, so who thinks that it decreases? Who thinks that it remains the same? Okay, so increase, decrease, same. Okay, I want to see your hands once more. Increase. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 25. Decrease. 2. Same. 3. Stay the same. 1, 2. Oh, there are around 50 students in the classroom. Okay, so why stays the same? Who said stays the same? Hmm? Now, I mean, we are talking about the moment of inertia, by the way, not the speed. So so I just open up my arms, so my moment of inertia increases, decreases, or stays the same. Yes. You still think that it stays the same? Yes. Okay, first of all, the moment of inertia, you can define moment of inertia. We define the moment of inertia without referring to the angular momentum. So you see, the moment of inertia we defined as mi ri squared, ri being the distance from the axis of rotation. So I want an explanation based on this, if possible. Same. Did you change your opinion? Yes or no? Okay. Which is also increasing. Okay. So it will be increasing. So you are saying that the various parts will now have a larger R, and hence they will contribute more. So you are saying that it is increasing. Okay, so that is one explanation. So, okay, who says it's decreasing? You? Okay, third one. Okay, anyway, that's basically the explanation. When you extend your arms or your legs, most of the parts of your body has the same R, they don't change. But some parts of your body, the arms or the legs, they move at a larger R. But since they move at a larger R, it means they are contributing more to the moments of inertia. If they are contributing more to the moment of inertia, I increases. So when you open up your arms, or open up your legs, your moment of inertia increases. Now, if the moment of inertia increases, L is equal to I omega. There is no external force acting on you. Well, at least negligible, let's say. There is negligible force acting on you. So angular momentum has to be conserved. If I changes from value I1 to value I2, angular velocity should also change. So if your moment of inertia increases, to keep this product constant, your W should decrease. So that is what we observe. Your friend, when she just stretched her legs, her moment of inertia increased, so her angular velocity decreased. And the other way around, when she gathered her legs, this decreased, so W1 has to increase. Now another question. Follow-up question. We know that the kinetic energy of rotation, we said that it is 1 over 2 I omega squared, which we can also write as 1 over 2 I omega squared divided by I, or L squared over 2I. Now we said that when she is gathering her legs, L is constant, this is constant, 2 is a constant, her moment of inertia is decreasing. That means her kinetic energy is increasing because L is constant. So she's just gathering her arms or legs. I decreases, so her kinetic energy is increasing. This is constant. So how come? Where does that energy come from? We say that energy is conserved. There is no potential energy change. All the motion is in the horizontal plane. There is no change in the gravitational potential energy. There is no other potential energy in the system. So how come the kinetic energy changes? What do you mean inertial energy? Well, we know the kinetic energy. That is what we have studied. We know the potential energy. I don't know what inertial energy is. So where does that energy come from? Let's do a simpler example. Imagine that you have a tube and you have a mass attached to a string that goes through this tube and it is rotating. That's the same system. Now, as you pull this string down, well, the angular momentum should be conserved. It means as it's getting closer to the center, its kinetic energy is W is increasing. But remember, I is decreasing, so the kinetic energy is increasing. Okay, that's true. As it's going down, so it starts to move faster and faster as it gets closer and closer to the tube. Why? So what is the source of that energy? And well, the source of energy is kind of obvious, F. But how come? How does F cause the increase in the kinetic energy? Now, that system is identical to this system. This system is more simpler. So at least we can identify more clearly what forces are. Okay, that is one possible explanation. We already, yes. So, it is perpendicular to the, okay, we should have more force, that's true. I mean, the closer the string is, the faster it will be moving, so the force we should apply should be equal to mv squared over L, or m omega squared L, whichever one you like. V is increasing, L is decreasing as you are pulling it up, so you have to apply a larger force. But how does that translate into kinetic energy? So let's remember one of the true and false questions in the exam. We had that the total work done on the system is equal to the change in the mechanical, is not equal to the change in the mechanical energy, it is the change in the kinetic energy, not the mechanical energy. So in this system, the kinetic energy is changing, so there should be some work done on the system. Well, the work done, the only thing that can do some work is F. How come that can do work? If it is doing circular motion, the force is always perpendicular to the displacement, so no work is done. Well, even if we just keep this string constant, the force constant, and rotate it, it is accelerating. There's always acceleration in circular motion. That doesn't mean we are doing some work. In uniform circular motion, in fact, we are not doing any work. I don't know. What do you think? Sure. This is for any work, for any motion, this should hold. The total work done should be equal to the change in the kinetic energy. How does it do work? I mean, you just said in circular motion, you say if you have a circular motion, the force is, the acceleration is in this direction, so that is the direction of the force also, but the displacement is in this direction. They are always perpendicular to each other. So there's no work done. Okay, that's true, but here we just said that the kinetic energy of the system is changing, it's increasing. So there should be some work done, and this force has to be doing some work somehow. But if these arguments hold for this case, then it's not doing any work. Okay. Okay, this is in the very small parts case. I divided my system into very, very small parts. In each one of these parts, the force is toward the center, this displacement is perpendicular to that one. In each one of these very small parts, there is no work done. Okay. Yes, we agree that it is doing work because the kinetic energy is increasing, but how come? I mean, you agree with this explanation, right? In circular motion, the central force doesn't do any work. Uniform circular motion. But here, how does it do work in that case, but not in this case? Is that uniform circular motion, by the way? It's not uniform circular motion. So this discussion is not really relevant. So the motion it will be doing will be effectively this one as it goes to smaller and smaller distances. So the velocity displacement also has a component towards the center. There is a displacement towards the center, so that will be doing some work. This one. So in this case, what we are doing is we are pulling down the string. So the radius of this string will get smaller and smaller as long as we pull it down. So the motion will not be circular anymore. It will spiral inside. So if this is the initial circle that is rotating, as we start pulling the string down, it will spiral inside. Then let's say we stop pushing it. But this means that its displacement is not perpendicular to the radial direction. It also has a displacement in the radial direction. The force that we apply, well, the tension force here that we apply is in the radial direction. There is a displacement in the radial direction. So there is work done on the system. There is positive work done on the system. So that since the work done is positive, the kinetic energy increases. The internal energy? Well, the energy is not conserved. We have external forces up here. So we cannot really talk about the conservation of energy here. The conservation of the energy of this one plus whatever is exerting the force is conserved. But then we have to discuss what is the rest. So what is the work done by this force? Can we calculate it? So on one hand, we know well, let's solve it. What is the change in the kinetic energy from the conservation of angular momentum? Let's just assume that initially it goes around the circle of radius L1. And when we pull it down, finally it goes around the circle L2. Now the change in the kinetic energy, or now I1 is mL1 squared, I2 is mL2 squared. Now conservation of angular momentum just tells me that mL1 squared times omega 1 should be equal to mL2 squared times omega 2. M's cancel. So the final angular velocity of this object is L1 squared omega 1 divided by L2 squared. The angular momentum of this object is m1 L1 squared omega 1, which is constant. And the change in the kinetic energy of the object, delta K, is the last kinet is the change in L squared divided by 2I. It is equal to L squared over 2, 1 over m L2 squared minus 1 over 2, 1 over m L1 squared. This is the change in the kinetic energy. Now, if we calculate the work done on the system, we should get the same kinetic energy, same change. Can we? Now, let's see how much work we have done. Now, for any L, any radial distance, this tells me that omega is equal to omega 1 L1 squared divided by L squared. This we will probably need it. Now, the motion was, okay, initially it is going like this, and then we change the force, and then it starts to go in such a circular orbit. Let's just divide this path into very small segments. This is my dl. This is the force that I am exerting on it. f dot dl is nothing but f times dr, the change in the radial component. Because this will just give me the component of dl in the along the force F, but that is just the radial displacement of my mass. Now, why did I put the minus sign, the absolute value sign? The force and the displacement are in the same direction, so the work is positive. But dr is a negative number, because the radius is decreasing. The change in the radial distance is negative. Minus F times R. dr, sorry. Now, the total work done is just the sum of the works in each one of these paths. So that will be minus F times dr. The radial distance starts from L2 and it goes up to L1. This is the work done. The only thing left is how to express the F as a function of the radial distance, the force that we have to apply. Now, we can just imagine that we are just pulling it very, very slowly. So at every instant, it will be, in fact, doing some circular motion. Since it is circular motion, the central acceleration is mv squared over L, when the radial distance is L. This should be equal to the force that we exert on my system. Now, V is equal to omega times, so let's see, the angular momentum, that will probably be much easier, is equal to, since it is doing circular motion, it is just L, this is the R. The force, the momentum is m times V. The angular momentum is given by this, LmV. So V is equal to L over m times small l. This is the angular momentum. So we obtain that the force that we should be exerting on my system, as I slowly pull it, is equal to m over the radial distance times the angular momentum divided by m times the radial distance squared. This is the force that I should exert, which is equal to L squared divided by L cubed. This is the force I have. This is the force that I should exert on my system if I want to slowly pull it inside. Now we are almost done. The total work done is equal to minus, this is the force, L squared divided by L cubed dr, and R goes from L2 up to L1. The integral of 1 over L cubed is, let's say, L squared over L. The integral will just give me minus 2, minus 1 over 2, L squared. L goes from L2 up to L1. This is equal to L squared over 2m, 1 over L1 squared minus 1 over L2 squared. dr, yes, dr is in fact dl. Why the sign mistake? That we have a mistake in the signs. We have a mistake because dr, the radial distance, or dl, doesn't start from L2, it starts from L1 up to L2. So this is L1 up to L2, L1 up to L2, so L2 squared minus L1 squared. Okay, now everything is fine. So we had calculated the work done by our force on our mass, and it is indeed equal to the total change in the kinetic energy of my system. So what we had done, our claim was this. It was just a claim. There is a force, as we are pulling the force so that our mass goes around smaller and smaller circles, that force is doing some work on my mass, and that work should be equal to the change in the kinetic energy. That was a claim up to this point. We didn't have any proof. That is something we expected based on our knowledge, because we knew that from the angular momentum conservation, the kinetic energy changed, and this was the change in the kinetic energy of my system as I just pulled it in. But if there is a kinetic energy change, there should be some force that is doing some work on the system, because kinetic energy change can only arise because of the force acting on the work done by forces. Now, the only force we had was this string that we were pulling. This is the only force we have. So if this does work, that should be the cause of the change in the kinetic energy. And we had to prove it. That was the claim up to this point. We said that, okay, this force is doing work, and that work is equal to the kinetic energy change. And we had to prove it. Now that is what we did. What we did was, okay, we just considered the trajectory, and we just assumed that we start from some L1 and just pull it down to L2 length. And this, for such a typical trajectory, the work done by in a very small segment was just F dot dl is F times the change in the radial distance, dr or dl. So this was the total work we had. F times dr, the radial distance, it changed from L1 to L2. Well, of course, this F also changed as one of your friends had mentioned. If we are pulling the force should be changing. We cannot apply the same force and keep pulling the mass inside to smaller and smaller circles. So the force should also depend on the radial distance. So we had to identify how are they related. Well, we know that v squared over L for any L is equal to the acceleration. If we multiply it by the m, it should be equal to our centripetal force. This is our F. So this identify how F depends on v and L. Well, the speed also changes as a function of L. So we had to identify how the speed also changes as a function of L. But for that, we can use the conservation of angular momentum. Angular momentum is just L times the momentum times the angle between them. But since we are here, we are just discussing the case when we are pulling it very slowly. At each instant, it is in fact making some circular motion. So the force and this dl, they are perpendicular to each other. So the angle between them is 90 degrees. Sine of 90 degrees is, no, not f, but the momentum and the radial distance, they are perpendicular to each other. The angle between them is 90 degrees. So sine of 90 is just 1. But this tells me that the velocity of my object at any radial distance, L, is just the angular momentum divided by the mass times the radial distance. If you just put it over here, it gives you the force as a function of the radial distance. And of course, the angular momentum, which is conserved. We know that this is constant. It doesn't change. This doesn't change. The only thing that changes is the radial distance. And we are integrating over the changes in the radial distance. So we just put this over here, integrate it over, and this is what we obtain. And the work done by the force, as we are just pulling it inside, it indeed turned out to be equal to the change in the kinetic energy of my system. So now our claim is proved. Before it was just a claim. Now we have the proof of it. Questions? Yes. Well, because by dr, what I denote by is the change in the radial distance. Since I'm pulling it in, the radial distance at the end of this pulling is smaller than the radial distance before. Radial distance is decreasing. So the change in the radial distance is negative. So initially it is here. After I pull it a bit, it is here. This dr is the change in the radial distance of my mass. But since my mass is approaching, going towards the center, the radial distance is decreasing. So dr is a negative number. This, with this minus sign, is a positive quantity. Because since dr is negative, I have another negative here. F is positive, this quantity is positive. As it should, because the displacement is in the same direction as the force. Other questions? Some last minute questions about any of the things we did today? About anything, not necessarily with this question. Okay, let's do Kepler's laws. Now this is the sun, and this is the orbit of the Earth. Let's just imagine that Earth at some point is over here. This is P. This is R. What is the direction of the angular momentum? Out of the blackboard. What is the magnitude of angular momentum? Sin theta what? It's not sine theta. R sine theta, no. R times P times sine theta. MRV sine theta. Now, if you go over our notes, saying when we were discussing Kepler's laws, Kepler said that the radius vector sweeps equal areas in equal times. That was one of the Kepler's laws, if you remember. And we had also analyzed it in terms of the kinematical variables, and we had shown that that law, in fact, just tells us that the radius of the planets times their speeds times sine of this angle theta is just constant throughout the motion. So Kepler's, I think it was the third law, just tells us that RV times sine theta is constant for during the motion of the planet. R changes, V changes, theta changes, but the product is constant. Now we see that that conservation is nothing but the conservation of angular momentum. Now let's see, what are the forces acting on the Earth? Gravity. Gravitational attraction of the sun. And there's nothing else. Of course, if we ignore other planets, well, weight is just a gravitational force. What is the torque created by this force for rotations around the sun? So one answer is 0. It is 0 because the angle between the r vector and the f vector is 180 degrees. Sine of 180 degrees is just 0. So the torque created by this force is 0, but that is the only force acting on my system. So the total torque acting on my system is 0, the total torque acting on Earth. But we have just seen that if the torque is 0, angular momentum is conserved. But angular momentum is just this product. If this is conserved, this has to be conserved. So we have the Kepler's third law. Now, L is conserved also for circular orbits. For circular orbits, the only difference is that R is just constant, theta is 90 degrees, V is constant. Circular orbits just means they are doing uniform circular motion. So conservation of angular momentum is not the reason why it's doing elliptic motion. But, well, I don't know if I answered your question. But any other question about anything else?